leisure, maybe your evening walk, or just your regular commute home from work.
Yeah, just your everyday routine.
Right, and you are passing dozens, maybe even hundreds of ordinary streetlights.
Most of us don't even look twice at them.
Exactly. I mean, we tend to view them simply as these tall, silent metal pillars just standing on the corner. We barely notice them unless a bulb is burnt out or, flickering annoyingly.
They're just part of the background noise of the city.
But those seemingly invisible pieces of everyday infrastructure are quietly undergoing a massive technological revolution. Welcome to this deep dive.
Glad to be here.
Our mission today is to uncover exactly how traditional street lighting is evolving into the ultimate eyes and brains of the modern urban environment.
We are really looking at a complete paradigm shift in urban infrastructure. I mean, the transition moves us from a reality where a streetlight is just a luminaire mounted on a pole to an environment where that same vertical real estate functions as a highly advanced integrated sensory node.
To map out this transformation, we are synthesizing a stack of specialized sources today. We are looking at an official technical code document from Malaysia's MTS-FB.
That's the Malaysian Technical Standards Forum, BHD, for context.
Right, which outlines the strict infrastructure standards required for this shift. We are also pairing that with a comprehensive project challenge proposal detailing the Favorite Urban Insight framework.
Which is essentially the analytical brain behind all these systems.
Exactly. And to ground all of this in real-world application, we are looking at use cases documented by Isersoft regarding the practical logistics of smart pole conversions.
Okay, let's unpack this. Wait, no, let me just say, okay, let's unpack this.
Yeah.
Because the problem with our legacy lighting infrastructure is deeply fundamental when you look at the operational needs of a modern city.
The Favorite documentation actually identifies a major blind spot in how urban environments have been managed up to this point.
And what's that blind spot?
Well, traditional street poles perform a single siloed function: illumination. That's it.
They just light up, right? They operate as if the city around them is entirely static. They cannot observe traffic flow, they fail to detect emerging congestion, and they are completely oblivious to safety risks or shifting environmental hazards.
So you have these massive, sprawling, highly dynamic urban centers, yet the primary infrastructure gridding the area is essentially blind and deaf.
Blind and deaf. That limitation creates a severe operational gap. City planners and emergency services, they need real-time situational awareness, but legacy infrastructure only provides a delayed, fragmented picture.
The solution bridging that gap is the smart pole.
Yes.
In both the MTS-FB standards and the Isersoft use cases, a smart pole transcends lighting entirely.
It integrates public Wi-Fi, CCTV arrays, and a whole suite of environmental sensors into a single multifunctional data collection hub.
From an engineering and urban planning perspective, it is a highly efficient utilization of existing space.
I mean, you are taking a vertical asset that is already positioned optimally every few dozen feet along roadways and pedestrian paths,
and converting it into a dense technological cluster. Here's where it gets really interesting. Cities do not always have to endure the massive capital expenditure of ripping up sidewalks and laying new foundational infrastructure to build these networks.
which is a huge relief for municipal budgets.
Definitely. Isersoft highlights that existing streetlights are prime candidates for direct conversion.
They already possess an established electricity supply.
And furthermore, these locations frequently run parallel to existing underground telephone and internet conduits.
Right, so the physical and logistical barriers to entry are significantly lower than installing new nodes from scratch.
That existing subterranean connectivity is crucial. The Isersoft documentation details a specific deployment in the city of Minster where this exact retrofit model was utilized.
Oh yeah, the parking lot example.
Exactly. An ordinary street lamp adjacent to a parking lot was converted into a smart pole specifically to monitor and manage that asphalt space.
It transitioned from a passive utility to an active management tool without requiring a complete teardown of the surrounding environment.
Beyond the expanded capabilities, the baseline function of providing light also sees a massive upgrade in efficiency, right?
Absolutely. These smart poles utilize advanced LED systems that ditch the standard inflexible timer relays.
So they don't just turn on at 6 p.m. and off at 6 a.m., regardless of what's happening.
Right. Instead, they dynamically adjust their luminosity based on real-time environmental variables. They can dim or brighten based on localized pedestrian foot traffic, time of day, and immediate weather conditions.
The return on investment there becomes a major driving factor for municipal adoption.
By dynamically responding to the environment, basically ensuring peak luminosity is only deployed when and where it is actively required. These systems drastically reduce baseline energy consumption,
That lowers both the direct utility costs and the long-term maintenance overhead.
effectively allowing the pole to subsidize its own advanced wireless and sensor payloads over its life cycle.
As you dig into the MTSFB technical codes, you realize that simply achieving this smart status is not the terminal goal of this infrastructure overhaul.
Not at all.
The Malaysian Technical Standards Forum, BHD, makes a very sharp distinction between a smart pole and an intelligent pole.
What's fascinating here is the philosophical shift this represents for city management.
How so?
Well, the NTSFB classifies a smart pole as possessing moderate intelligence. It houses the cameras and the IoT sensors, but its primary function is data collection.
It operates as a standalone unit or ties into a very basic, localized system to improve baseline infrastructure efficiency.
Exactly. It records the telemetry, but it does not possess the onboard compute to act upon it.
It functions essentially as a high-tech diagnostic tool.
Right. It can tell the central database that traffic is backing up, but it relies on a human operator to notice the alert and manually change the traffic light phasing.
But the leap to the intelligent pole changes that dynamic entirely.
It does. The MTSFB defines intelligent poles as featuring high AI-driven capabilities. They move beyond passive data collection into real-time analysis and autonomous decision-making.
Fully integrated into a comprehensive smart city platform.
That integration is what allows a municipality to transition from reactive infrastructure management, which is basically reviewing data to understand what already occurred, to proactive, data-driven governance.
We are looking at a framework where real-time surveillance and environmental telemetry are utilized to actively and instantly alter the urban environment.
Let's contextualize that difference for a second.
Okay.
Imagine you have a standard smart pole at an intersection and a traffic collision occurs. The pole records the incident. A city operator might review that footage later to understand the cause, or perhaps notice the alert a few minutes later and dispatch emergency services.
That is a reactive posture.
Right. Now, place an intelligent pole at that same intersection. The onboard AI instantly detects the collision anomaly.
In milliseconds.
Yes. It autonomously alerts emergency dispatch, automatically dims the immediate surrounding streetlights to a warning frequency for oncoming drivers, and communicates with traffic signals several miles upstream to reroute incoming vehicles and prevent a secondary gridlock.
The infrastructure adjusts instantly to manage the aftermath without waiting for human input.
The raw telemetry is put to work the millisecond it is generated.
But achieving that level of autonomous response requires a massive computational backbone.
Capturing millions of data points every second from a grid of thousands of intelligent poles will simply overwhelm a city's network if there isn't a highly structured, systematic way to process and route that information.
That operational necessity is exactly what the Favorite Urban Insight Framework addresses.
The Favorite framework essentially acts as the cognitive processing center for the hardware.
It is structured as a step-by-step methodology to transform raw, unstructured data into actionable municipal intelligence.
It maps this out across specific layers, beginning with what they designate as Layer 0, intent and context.
Before a city deploys a single piece of hardware, they must strictly define the urban challenge.
The Favorite proposal highlights systemic issues like limited real-time visibility, sluggish incident response times, and a severe deficit in localized environmental data.
So the deployment must be anchored to a specific operational outcome.
You cannot simply deploy sensors for the sake of having sensors.
Right.
Once the operational intent is established, the framework moves to Layer 1, the data foundation layer,
This is the hardware capture phase.
acting as the city's newly deployed nervous system. You are looking at specialized video analytics cameras tailored for continuous monitoring of traffic flow, pedestrian kinematics, and crowd density algorithms.
But the optical sensors are just one piece of the puzzle. The broader IoT payload on these poles is extensive.
They are actively measuring localized concentrations of fine particulate matter.
Like PM 2.5.
Exactly. Tracking CO2 levels, monitoring acoustic pollution via decibel sensors, and recording microclimate data like temperature and humidity.
And alongside the sensors, you have the integration of public-facing utilities, Wi-Fi hotspots, EV charging interfaces, emergency duress buttons, and localized public announcement systems.
All of this telemetry has to be streamed securely back to the central platform.
Utilizing standard IoT protocols like MQTT or HTTP.
Those protocols are vital. When you are dealing with thousands of nodes transmitting constant microbursts of data, like a 1-degree temperature shift or a single vehicle count, you rely on lightweight messaging protocols like MQTT.
It ensures that telemetry reaches the platform reliably without saturating the city's available bandwidth.
Because without that highly scalable, secure data foundation, the analytical layers built on top of it will inherently fail.
Once that data foundation is securely capturing the environment, the immediate challenge is making sense of the influx.
Which is where layer 2 comes in.
Favorite structures this next step as the descriptive insights layer. The primary objective here is answering the immediate question, what is happening right now?
The descriptive layer focuses on data visualization and situational awareness. It takes those millions of raw MQTT payloads and translates them into a format that a human operator can quickly interpret.
The favorite documentation details comprehensive visual dashboards utilized by city managers.
The visualizations allow an operator to pull up a live air pollution heat map layered over specific urban districts, rather than just looking at a spreadsheet of numbers.
They can view exact real-time vehicle counts per intersection, map out peak traffic density curves, or instantly verify the operational status and power draw of the smart poles themselves.
It grants total situational awareness across multiple municipal zones simultaneously,
eliminating the need to physically dispatch personnel just to assess current conditions.
But while visualization is necessary, it only provides the surface-level reality.
Understanding the underlying mechanics requires moving to layer 3, the diagnostic insights layer of the Faviate framework, which seeks to answer, why is this happening?
This is the stage where the platform begins cross-referencing the siloed data streams.
Right, connecting the dots.
This raises an important question. How do you reliably correlate an acoustic spike with an optical anomaly?
The diagnostic analytics engine within Faviate is designed to combine disparate data sources to uncover hidden operational patterns.
For instance, the system registers a sudden, localized spike in atmospheric pollution. By cross-referencing that environmental telemetry with the video analytics feed from the same node, the platform reveals that the pollution spike perfectly correlates with an unexpected period of intense traffic congestion at that specific intersection.
The Faviate proposal outlines several of these cross-referenced scenarios.
The system can overlay decibel readings from the noise sensors with the optical crowd density metrics in an entertainment district,
to determine if a gathering is standard nightlife activity or a developing volatile situation.
Exactly. It can identify abnormal kinetic behavior in the traffic feed, like sudden, coordinated braking or vehicle swerving, that serves as a diagnostic indicator that an accident has likely occurred.
Even if the impact itself wasn't captured on camera.
Instead of just reacting to the symptom, operators gain visibility into the root cause.
When a system accurately understands the root cause of an event and has accumulated a vast repository of historical data regarding similar events, it unlocks the capability to forecast.
That transition marks layer 4, the predictive insights layer within the Faviate methodology. The operational focus shifts entirely to answering what may happen next.
The predictive layer relies heavily on advanced AI modeling.
By analyzing historical time series data and feeding it into machine learning algorithms alongside the live telemetry feeds, the system begins forecasting urban conditions before they physically manifest.
The source documentation provides some compelling use cases for this capability.
The intelligent poles can analyze current pedestrian flow rates and historical event data to accurately anticipate severe crowd density choke points before a major festival or public gathering even begins.
The operational advantage of that forecasting cannot be overstated. It allows a municipality to completely abandon reactive crisis management in favor of proactive mitigation.
If the predictive models indicate that a severe traffic gridlock is statistically likely to build up in a specific corridor within the next 20 minutes, the system can preemptively adjust the traffic signal phasing upstream to bleed off the volume before the congestion ever materializes.
If the models anticipate a massive crowd forming in a poorly lit area, it can activate dynamic, high-intensity street lighting well in advance of the influx.
It keeps the city's infrastructure operating one step ahead of the physical reality on the ground,
which seamlessly transitions into the final, most critical component of the framework, Layer 5, prescriptive insights.
This layer is dedicated to answering what should be done.
It represents the translation of predictive intelligence into concrete, automated action. Favorite utilizes complex rule engines and automated workflows to trigger operational responses without requiring a human operator to manually authorize the action.
That automation layer is where the true value of the intelligent pole is realized.
If the environmental sensors detect that localized pollution thresholds have been breached, the prescripted engine automatically generates and routes alerts directly to the relevant environmental agencies.
If the internal diagnostics of a streetlight indicate a hardware malfunction or an impending bulb failure, it autonomously schedules a maintenance ticket and routes it directly to the repair crews.
If the kinetic anomaly models detect an accident, the coordinates and visual feeds are instantly pushed to the city control centers and emergency dispatch.
The prescriptive capabilities extend far beyond immediate emergency response. They deeply influence long-term urban planning.
The favorite documentation notes that city planners utilize this aggregated, analyzed data to identify specific corridors that statistically require additional pedestrian crossings based on actual measured foot traffic and near-miss vehicle data.
Planners can use the environmental mapping to design specific road redesigns in high accident zones or model structural changes aimed at improving urban ventilation in identified pollution hotspots.
We are seeing data literally dictate the future flow of concrete and asphalt.
The infrastructure is no longer just sitting on the environment. It is actively shaping how the environment will be built in the next iteration.
So what does this all mean? When you synthesize these three specialized sources, a very cohesive architectural roadmap emerges.
You have the Isosoft use cases, demonstrating the logistical viability of retrofitting ordinary lamps to handle smart parking management and security deterrence.
You have the favorite proposal, providing a highly robust, multi-layered analytical framework to capture, diagnose, predict, and act upon the massive influx of data.
And providing the structural integrity for all of this, you have organizations like MTSFB, establishing the strict technical codes and standards.
The MTSFB standards serve as the critical foundation. We are discussing the deployment of a massive, heavily saturated, citywide radio communications and edge computing infrastructure.
Setting rigid technical codes ensures that as these proprietary networks scale across millions of vertical assets, they remain secure, structurally unified, and fully interoperable.
You cannot have a scenario where a newly installed traffic camera is broadcasting in a digital protocol that the legacy environmental sensor network cannot parse.
The standards ensure the entire urban nervous system speaks the same language.
Precisely.
If we connect this to the bigger picture, if we connect this to the bigger picture, we are observing the definitive end of guesswork in municipal governance and urban planning.
For centuries, cities were expanded, zoned, and managed based on intuition, delayed reporting, and static census data.
That era is closing. Urban management is becoming an exact, real-time science.
The infrastructure itself is adapting seamlessly to the immediate physical and environmental needs of the population, continuously operating right above our heads.
It is truly a quiet revolution.
We have tracked a fascinating evolution today. We've moved from a simple, isolated light bulb on a stick, a piece of legacy hardware designed over a century ago, with the sole basic purpose of pushing back the dark, to a highly integrated, autonomous, AI-driven urban node.
It really reframes how you look at the street.
The next time you walk down a lit street in your city, remember that you are no longer just moving through a static, silent environment. You are physically interacting with a responsive digital organism that is continuously observing, calculating, and adapting to the world around it. Thank you for joining us on this deep dive.
It has been an absolute pleasure analyzing this evolution with you.
Before we sign off, we want to leave you with one final thought to mull over based on the trajectory of this technology. We have spent this time detailing how these integrated systems optimize our traffic flow, monitor our environmental health, and coordinate our emergency responses. But if the ultimate endgame is that every single street pole becomes an intelligent, listening, and watching node optimized for our physical safety and convenience, how will that omnipresent, overlapping digital safety net fundamentally alter our expectation of privacy in public spaces? As these networks scale to cover every inch of the urban landscape, will we come to view our city streets as a helpful, protective guardian, or as an unblinking, unavoidable observer? Something to consider on your next evening walk. Take care.